pleasure to be here, as everyone said, but I want to repeat it again. Thanks for the organizer. So now I will talk about, things that we have all talked about before, planetary climates, habitability. And at least at the beginning of my talk, I will talk about habitability, and I hope in a way which is not controversial. So I'm very curious if someone here in the room really disagree. For the first slide, just say it, and we can. I will skip slide at the end if necessary, because I hope to say something that everyone agrees with. So here is what to start with. Of course, habitability is a question of life. So we have to define life. It's impossible. We can imagine any kind of life in plasma, whatever. What's needed for life, we don't know. But the story, when we want to use the concept of habitability, for instance, to prepare observations, is that we have to find something that you can, for instance, recognize. So the assumption is usually that we have a carbon-based chemistry, and in particular in liquid water. If you have been to similar meetings, you have heard, maybe not this week, many times that it's difficult to imagine a carbon chemistry rich enough for life without liquid water. But the real key point, in my opinion, is that life without liquid water is difficult to recognize and detect. And that's the thing, when we use this concept of habitability, in some way, we don't want to be chauvinistic with regard to life, but it's because we want to prepare future observations, how to look for extraterrestrial life, and so something we can recognize. Of course, on Titan, it is very fascinating to imagine a rich chemistry that could provide life, but it's not easy to recognize, especially when you are at several light years. So ultimately, as you all know, physicists have always used this trick to say that habitability, can you hear me well? Habitability is where you have liquid water available, and of course, that's the minimum for life as we can imagine it. But the problem is that some habitats, some habitable planets are more habitable than others. We all know that. I hope everyone agrees. First, it was mentioned this week, we need something which has a certain duration. Time is required for life to emerge. In fact, we don't know, but maybe, and evolve. And on the Earth, at least, it takes billions of years to reach multicellular species, and even more to build radio telescope. And also, of course, you have the quality of habitability. That's something I don't know much about, but of course you need chemical species, nutriments, and something which is very important. You need energy, and in particular light. And astrophysicists has been assuming that light was very important because the energy that has been used by the life on the Earth to transform the environment in a detectable way is really through photosynthesis. So that is why many astronomers are biased and look for surface life. I will come back to that. But before that, I want to advertise some concept that have been put forward in a paper by Helmut Lammer. I also advertised that in my paper in 2013. This idea that maybe you can define 4 kinds of habitability. And I think it's a useful definition. The first class, of course, will be planets with permanent surface liquid water like the Earth for billions of years, let's say. Class 2 will be, that's an important planet which will be temporarily able to sustain surface liquid water, but which lose its stability. That must be a current something which is quite common. You can lose that because you lose the atmosphere, the star evolve, whatever. So that could be the case of Mars, of course. We will hear more about that this afternoon. Even Venus, there are speculation, not proven at all, that there could have been an ocean initially. Then you lose the ocean, and now you can speculate. No one really believed that, but this life was able to evolve and survive in the water, H2SO4 and liquid water clouds in the atmosphere. It's a speculation, but you see the idea. Class 3 is body with surface oceans which interact with a silicate mantle. We heard about Enceladus yesterday. Europa, of course, you have lots of examples, but this is below the ice. It's dark, But you have some nutriments. You have some volcanic activity at the bottom. It's very good. But you have even worse than that. You're in the dark. But if you have a big enough planet which is icy, coming from beyond the sunlight, if you want, in the traditional view, you can have, if you have a thick enough subsurface ocean, you have ice at the surface, and at very high pressure, another phase change, so that the ocean that you get, for instance, Ganymede, is thought to be sandwiched between two ice layers. And then it's not easy to have lots of nutriments. It's just speculation, but that's a way to classify that. I hope that we can put all the things you have in mind in this class. In practice, of course, when you're an astronomer and you want to look for life in exoplanets, it's not easy to detect this. And we tend to concentrate, of course, on class 1, the surface liquid water on the day side that can benefit of light. So the surface liquid water allows fantastic life, which is able to modify its environment in a detectable way. So that's the traditional habitable zone. We call it surface liquid water habitable zone. Or François suggesting to keep the acronym HD and call it the hunting zone. So the habitable zone is not where you can find life or where life can exist. It's where we think you can you should target your telescope to look for a life able to change the environment in a detectable way. So it's just that, the habitable zone. It's not more than that. But it's a definition which is where liquid water is possible on the surface of planets for any kind of atmosphere. You cannot say the habitable zone change if you have a thick atmosphere or a thin atmosphere. It's not true. The idea, let's put it that way, the habitable zone is a region outside which it is not possible for a rocky planet to maintain liquid water on its surface. If you're outside, in my view, it could be a good way to define it, and you will see you have some caveats. The definition of the habitable zone could be that outside it, whatever atmosphere you assume, it's not possible to have liquid water on the surface, whatever the atmosphere. And of course, we all know that if you're in the habitable zone, that doesn't mean you're habitable. The moon is not habitable. It's obvious. But the idea is that if you have a planet outside the habitable zone, it's almost impossible to have liquid water on the surface. So ultimately, habitable zone, this problem of habitability, surface habitability, is a problem of climate and atmosphere. And to study that, you have various tools that have been used to study that. You have a hierarchy of models, if you want. Historically, and you can still do great science with that, you have the 1D global relative convective models. These are still used to define the classical habitable zone I just talked about, the work by Jim Casting, of course. And this week, for instance, Barbara Strack used such a model to explore the habitability on a fixed lead planet. No, how do you call that? Stagnant lead planet. You have 2D energy balance model, don't use much anymore. You have theoretical 3D general escalation model. If you go to extrasolar planet meetings, you will see a lot of talks using 3D models, but with very simplified forcing in terms of relative transfer or temperature contrast. They are designed to explore atmospheric circulation, maybe heat transport. And I think Ludmila Caron, in the week later today, will use such a tool to explore the heat transport on TRAPPIST planets. And then you have a fourth kind, which are the full 3D global climate model that I'm going to talk about, which are super ambitious. These are models that pretend, that aim at building virtual planets that are able to simulate everything that is going on the planet and simulate it realistically, everything you could observe, only based on universal equations. So of course it's super ambitious, you may say it's naive, but doing that you learn a lot and sometimes it works. So how is that possible? Of course, when you look at this image for the Earth, you could say the complexity is enormous. You have millions of degrees of liberty, coupled system, and you will think this is really too complex to model. But in fact, this image actually is coming from a model, a very standard climate model that is used on the Earth to simulate climate change and even weather forecast. And we could do that on other planets. So how could you do that? In fact, the reality is that all this, even on the Earth, is controlled by a limited number of differential equations, if you want, that control everything. So you have millions of the reality, but the number of equations, physical process, is limited. So in practice, you can develop such a model by, if you want, just putting a few bricks to solve the differential equation. So they're not like that. In practice, this is what you need to build a climate simulator. You need, I will go fast, you need a dynamical core to solve the atmospheric motion and transport. Then at each grid point of such a computer model, you have to solve the relative transfers with the gases and the aerosols. You need to represent the turbulence, which are not represented by the big grid. Surface thermal balance, that's very simple. More difficult, the volatile condensation, even the oceans and so on. And sometimes you have photochemical hazes and lifted mineral aerosols typically. And if you take all that, you can do a lot, almost simulate any planet. We, in our group at LMD in Paris, we've done that for every terrestrial planet that we have in the solar system: Mars, Venus, Titan, Triton, satellite of Neptune, and even Pluto. We also are working on Saturn and Jupiter right now. And what we have learned a lot. What we have learned is by many measures, the GCM work. Frankly, it's quite fascinating. It's actually fun to put the equations, create a sphere, put CO2 on it, rotate it, watch it, and you have something close to Mars. You have something close to Venus. It works quite well. Of course, very often it fails. You have something we disagree. And we learn a lot. If there is a physical process missing, if you have nonlinear process, we learn a lot how to complement that or how to bracket the reality by playing with parameters. And the third lesson from the solar system is that climate model components can be applied without major changes to most terrestrial planets. For instance, the dynamical core has been pretty good, or the turbulence scheme that we use, the mathematical beast, works very well on Titan. It had been able to predict very well the structure of the boundary layer on Titan without almost any change. So this gave us some confidence. We're not naive, but at least it's a good tool. So what can you do with that if you take all these bricks, put them together? Some people can simulate anything. Some people suggested to simulate the Middle Earth of Tolkien, but what we can do better, we can create one model to simulate them all. In other words, we have created a generic global climate model. Oops, sorry. Again, solving all the things that I put there, and for each cases, we have developed a version that is very flexible. I won't detail that, of course, it's a little long. The key point is that it's a lot of work for the relative transfer because you need to develop relative transfer code, able to solve relative transfer through any mixture of gas and aerosols you want, but fast enough to work in 3D. But that's something we did some time ago. And with that, we can play a lot with various atmospheres. So let's go back to my subject. Now, with such a tool, you can take any atmosphere you want, any gas, anything. You can use the stellar insolation you want. Very often for observed extrasolar planet, you can know what is the stellar insolation. In some way, you know the orbit, you know the eccentricity, you know things. You can know somewhat, or you can speculate on the rotation, the obliquity as well. And then you have to completely speculate now on the atmospheric composition and the surface volatile inventory. But if you assume all that, using the climate model, you can simulate the climate and, in particular, explore the surface habitability. So when you do that, typically you always reach some problem when you reach the edge of the habitable zone. And this is where it's interesting. For instance, if you take the Earth and you move it close to the Sun, where do you start having problems? And the answer, as you probably all know, is very quickly. If you have any planet with surface oceans, let's say, if you move it a little bit toward with the flux higher than on the Earth, you have a problem because of the famous process of Runner greenhouse effect. You increase the flux a little bit, temperature increase. If you have liquid water on the surface, that's what you want for habitability. You increase the evaporation, you have more greenhouse effect due to water vapor, and you increase the surface temperature. And this is a very strong positive feedback, so that, and that's been known for a while, this is a result from a 1D model. This great work by, you have pioneer work by Ingersoll or Catherine Deberg, for instance, and Razul. But then the reference work is by Casting, and now it's a former student Koparapu and so on. This is you probably have seen this plot before, but this is when you assume a given relative solar luminosity. This is where the Earth is. This is the surface temperature. Earth, of course, is at 15 degrees Celsius, but if you increase a little bit, very quickly because of this effect, poof, you have a temperature of the surface of 2000 Celsius. All the oceans are vaporized in the atmosphere, super strong greenhouse effect. It's a very strong instability. I mentioned to you that we're working now with 3D models, and we've done that. This paper, this is figures from a paper by Jérémy Lecomte using the LMD model in 2013 in Nature. And we have tried that in 3D. And we were very interested to see, it was interesting to do that. You have to do a lot of development because you suddenly, water vapor can become a major constituent of the atmosphere. You have very tricky processes controlling the pressure with the water vapor. It's very not extraterrestrial, but we did all that. It was interesting. And we were expecting to really change the story because, for instance, in 1D model, clouds are neglected. We expected that clouds could protect the planet and we could move closer to the sun. That's not what we found. We found that clouds were high, actually increasing the greenhouse effect. But on the other hand, we also found that nevertheless, the 3D models assume that the limit will be a little closer to the sun, not much, so we were no big change. Instead of 0.97 AU at the time, it was 0.95 AU. And the reason was not because of clouds, it's because, let me show you, for instance, output from a simulation. The relative humidity, which is always assumed to be near 100% or 90%, is actually not that high everywhere. And in the tropics, because of descending motion, you have unsaturated tropical regions, which really reduce the greenhouse effect, and you have radiative fins. But this is detail. I just wanted to give you a flavor of the kind of work we can do. You can also explore what's going on if you go close to a smaller star. Of course, around M dwarf star, typically, the spectrum from the star is redder, even in the near-infrared. That changed the story because you have a weaker Rayleigh scattering. The atmosphere reflects less energy, so you heat more, so you have to be, in terms of flux, you have a little further away from the star, but it's not that big. And the other key point is that very often, as you probably all know, when you are around the M star and you are in the habitable zone, you have a strong effect of gravitational tides that really, for instance, put your obliquity to 0. So you have, it's always cold at the pole. That can be useful. And you also have possible locking with permanent night side. Whatever happens, you tend to rotate very slowly, for instance, like Mercury if you're in a resonance, or locked like the moon around the Earth. And if you simulate this climate then, and that's a simulation by Jérémy Lecomte, imagine you see a planet from far away going around the star. What we found in that case, unlike for the Earth's case, this time the clouds tend to form only on the day side. You have strong convection, strong heating, and these clouds really increase the albedo on the day side where the sun hit, and that really helped to protect the greenhouse effect, and we found that it will really prevent heating. This time it's a big change compared to the traditional 1D view. In fact, we found that, Jérémy found that. This is a schematic drawing to explain the story. But it was actually found even before by Yun Yang and in the team of Dorian Abbott at the University of Chicago, and they published that stabilizing cloud feedback dramatically expands the habitable zone of tidally locked planet. Dramatically expand, if you are seen from far away, it's not dramatic, okay? It moves the edge of the traditional shape you see for the habitable zone a little closer. For us, it's dramatic, but you cannot go very near the sun, don't worry. Okay, how much time do I have? So now let's move to the other side, cold planets, the outer edge of the habitable zone. First south, as you know. When you move the Earth further away from the sun, as it has been mentioned this week, you also quickly reach a limit of habitability. because of another feedback, the Renault glaciation. If you decrease the solar flux, temperature decrease, you have more ice and snow, the albedo increase. That means you cool the planet and so on. You may have heard about it, but it's fun to watch when you do it in a 3D model. This is an output from a simulation by Benjamin Charnay, who is in this room. You take the Earth, you move it suddenly by 12%, what happened? What happened is pretty violent, it's very quick. So this is a map of the albedo. You see the ice and the snow. Oops, and you start. You start the simulation, and very quickly, the feedback I just mentioned will be very efficient. You will have snow on the continents. The sea ice will move. This is only after 6 years. And the albedo of the planet will increase. You cool the planet, and after you can see the tropics try to resist, but that doesn't last long. Even if you move the Earth less, it works like that. And after only a few 25 years, let's say, in this simulation, of course, you completely freeze the planet, and then it's irreversible. And second, even in Queenon, the temperature will be minus 40 on average. And it will be minus 60 in Paris or whatever you want. So it's a very different planet. It's the famous feedback. Of course, we all know that moving the Earth by 12% is like putting the insolation from the sun 3 billion years ago, when the sun was younger and faint. So, of course, there is a solution. If you increase the greenhouse effect, and not much CO2 more can really prevent the full glaciation, and a little bit more, it can allow the glaciation. So the key question, of course, for that you need the carbonate cycle. I don't have time, really not going fast enough. Then the question is, if you back to this definition of the habitable zone, how far can you go and still have liquid water for any atmosphere you can imagine? Well, for pure CO2, there is a limit, because you cannot add eternally CO2. After a while, you saturate this greenhouse effect. In fact, you increase the albedo of the planet by adding atmosphere. There is a maximum around 10 bar, and at 10 bar, you can go all the way to 1.7 AU, but pure CO2, you won't be able to warm the planet more. You can speculate that you can do more with CO2 ice clouds, maybe all the way to 2.5 AU, but this was, I think, this is something we published in '97. But in fact, we don't believe really anymore, because in 3D, the clouds coverage is not perfect. Nevertheless, 2.5 AU is in some way a complete limit. Whatever greenhouse gas you put, realistic greenhouse gas, even if you assume that extraterrestrial will put very super efficient greenhouse gas, it's difficult to go beyond that. The flux is really low. There is one exception, is if you assume that you can have hydrogen-enriched permeable atmosphere. In that case, H2, it turns out, if you have a lot of H2, is a very efficient greenhouse gas. It does not condense, and you can find that if you have 100 bar of H2, so what kind of planet is that? Can you keep it if you're a terrestrial planet? There's lots of speculation behind that. Are they possible? Then you can have a very extended habitable zone. So that's the caveat I mentioned. With traditional atmosphere, we limit the habitable zone at maybe 2.5 AU from the equivalent from the sun. But with H2 atmosphere, recent studies have shown that you can really go further away, but these are different animals in some way. But this is an interesting point. Okay, around K and M dwarf stars, I will actually skip that because I don't have much time. It's about the same story. Of course, there were a key problem due to the locking. If you have a permanent night side, you can wonder, in such cold condition, if you would store, all your volatile will be frozen on the night side. This can be studied a lot. We did, as was mentioned, a speculation with Gliese 581d some time ago. We did a lot of work, lots of simulation, which are fun to watch, with CO2 ice clouds. And we found that it was working very well for various reasons I won't detail. At the time, as was mentioned by Alain, we were proud to announce that 581d was the first discovered terrestrial planet in the habitable zone. Not habitable, but in the habitable zone as we define it, because of various processes that were neglected before. But ultimately, of course, it was found that the Gliese 581d does not exist, although there were some debates, but I think it does not exist. So no more of this one. Okay, that's the traditional habitable zone. Again, my key point here is that don't not assume that atmospheric scientists are dummy and there must be a way to have a habitable planet there. With oceans or even lakes, it's almost impossible. Same thing here. Unless you have hydrogen atmosphere, it's almost impossible to have liquid water on the surface there with a standard atmosphere, whatever greenhouse gas you assume, except H2. So this is the middle of my talk. The big conclusions. For given parameters of atmosphere, global climate models are fit to explore, we think, the thing. But the real problem, in fact, so you have two problems. First, of course, you have this instability, which are extremely difficult to deal with. So you have to explore parameters to bracket the reality. Otherwise, you're super naive. But the real problem is the atmospheric composition. It's a key problem. We don't understand what's really controlling the composition of the atmosphere. Our experience in the solar system is not sufficient. If we didn't have Venus, I'm not sure we will dare imagining Venus. If we didn't have Titan, we just will not imagine it. So we need more observations. We've been speculating. This is a plot from Forgy and Leconte in 2013. French people may understand that we call it the Davis Cup 1991 paper. And this is a plot where we try to speculate about all the possible major dominant species as a function of planet mass and stellar flux. This is pure speculation, and in some way, this plot, I won't have time to detail it, is really designed to prepare the surprise that we will have when we have true observations. Another example I can give you a flavor of is, for instance, when you deal with this very exciting case of Proxima Centauri B. There will be a talk next door by Amory Vandal. It's a super Earth, not that big, with just 65% of the flux on the Earth, probably in slow rotation. And there, Martin Turbet, who's in the room, did a lot of simulations with our 3D model to explore the habitability. But it was a problem because we didn't know at all what was on this planet. So what he did is explore various kind of amount of atmosphere, nitrogen, CO2, and various amount of water available. And when you do that with a lot of simulations, all the stars here are simulations, you find a lot of possible climates, depending on the CO2 partial pressure you assume. It's not that sensitive to nitrogen, and the surface reservoir you put. So that's a schematic drawing, but it's based really on pretty complex, long simulations. So I won't have time to detail. Let me just one example is that if you have a lot of water, you will have kind of ocean, and with such a planet, almost whatever the atmosphere you choose, you will be habitable. The reason is that if you have lots of greenhouse gas, we have a warm climate. If you don't have much greenhouse gas, then you have a frozen night side if you're in synchronous rotation. But this is an example here, frozen night side, but here you can see the dashed line here is the boundary of the ice. You will have what we call the eyeball planet, and you have open water on the day side. So if you look at this paper, I recommend, you will see that there is a wide range of parameters for which it's exciting. Proxima B could be habitable, and we're not that naive. It's really not easy to maybe there's no atmosphere. Problem done. It's possible. It's M dwarf, very active when it's young, and so on. Okay, I'm just reaching my conclusion. Don't worry. And the key point of my conclusion, you can read it. The key point is that models are good. We're not naive. They're not perfect, but they can explore things. But what we really don't know is the zoo, possible zoo of atmosphere we can have on these planets. To work on this investigation about the likeliness of habitable planet and so on, what we need to understand is what controls the atmospheres. Even observations well outside the habitable zone would be interesting. We need to understand the process, escape, outgassing, feedback, and so we need observation atmosphere wherever they are. So that's my conclusion. Thank you.
Thank you.